Okay. So for the training process, right? So basically, we kind of follow these steps, right? We sample the label data into a batch, which I'll talk about in the next slide. And we forward these images through the network, get the predictions, and we can compute the loss, right, for each of these images in this batch. And we back propagate this error, right, and trying to update the network's weights. Okay, so the next time, hopefully, when the weights get updated, the network is able to make less error, right? The loss can be reduced. Okay. So graphically, you will see, right, this is kind of like the loss landscape, right? In the beginning, maybe you have, because of the weights are randomly initialized, right? You have a very high loss, but over the course of optimization, hopefully the loss will, gradually decrease, and eventually maybe you are reaching at a local minima. Okay. So the method we used for optimization is the gradient descent, right? So this is widely used for doing the optimization, and this is also used in logistic regression, linear regression as well. So basically, you have, when you specify objective or cost function, right, or loss function, J theta, right here, and here are the steps you can follow to update the parameter theta. Okay, so in each of the iteration, right? So we have a theta new to indicating like the updated parameter value. So that is the theta old minus alpha times the gradient or the derivative at this point. So alpha is a learning rate. Okay, so this is a positive value, which is also a very important hyperparameters we have to tune, right? What learning rate we need to use. And this is the derivative, okay? And then then you can do this iteratively, and so hopefully you can reach a threshold, right? So if there's not much change in terms of the parameter, right? So the previous iteration and the current iteration, the alpha value doesn't change too much, and then you can, to a certain threshold, you can say, okay, we can stop here. Or the loss doesn't change too much, then we can, stop the training. So a couple of things I want to mention is this minus sign here. So you may wondering, right? Why do we minus this learning rate times this gradient? So here I put a very simple graph illustration here. So this is the loss, the cost function, right? So this is in terms of the theta. Okay, so here we can say this is 0 and this is the positive side. So let's say if the loss function or the loss curve looks like this, okay? And let's look at one. Let me get the laser point here. Okay, so if you end up here, right? So let's say at this stage, your theta is here, okay? And if we compute the gradient, right, the derivative, right, which basically is the slope right here, right, we get a positive, right? So it's kind of, tangent value here. So it's going to be a positive value, right? And we look at what is the closed, local minima, which is here, right, marked as X here. So I think the goal here is let's try to get to this local minima, right? Because this is going to be minimize the total cost function. So we're trying to go towards the left side, right? Make the theta to a smaller value, right? So here, so we have this alpha is always going to be a positive value because of a learning rate, right? So we minus a positive slope, right? The gradient. We end up with a new theta, which is a smaller value, by kind of trying to get to this local minima, okay? So this is valid, right? But if let's say we have another scenario, right? We have a maybe here, right? The alpha value is right now is here, and if we want to get to local minima, right? Seems like this is the closest one. We can go from here, but it's much easier to go to this local minima, right? Because we only have a couple of steps we can reach there. But here you kind of go up here, then go downhill, right? So let's look at, say, the goal is to reach this local minima, which is marked at x here. And if we compute the gradient, the slope here, right, we have a negative slope, right? So here we have a minus sign here, and then which means we plus some value here. Then we end up, the new parameter is going to be a larger value as compared to the old one, right? So we move to the right side, okay? So again, we are towards the right direction, right? Because we want to move to the right side so that we can reach to this local minima, okay? So that's why we have this minus sign here for the gradient descent, okay? So this is one for one particular neuron, right? Because of the network, we have many parameters, right? So at different layers and different neurons in each of the layer. So the way we compute the gradient at each of the location is we can apply the chain rule. So basically we can multiply them different positions together to get the gradient for each of the neurons using the chain rule. Okay, so that's the basic mechanism to optimize the network parameter, right? By specifying the loss function and using the gradient descent to minimize the loss or the cost of the function. And we also talk about the one important component in the deep neural network is the activation function, right? We have this 10H sigmoid and ReLU or maybe other variants of value. So this is the curve for the ReLU function, right? So basically take the max of 0 and the input z, right? So this is what the curve look like. So if we compute the gradient, right, the derivative, one potential problem is the vanishing gradient problem, right? So here on the left, on the negative side, we always have the value of 0, right? We end up with the gradient of 0. So we need to try tackle this vanishing gradient problem. So one way is we can make some adjustment to the left side, right? This kind of parameterized ReLU, right? Have a small slope on the negative side. Rather, you kind of force them all these equal to 0. So this is another way, to kind of solve this vanishing gradient problem. And so we talk about the gradient descent, all right, to optimize the network or the training process. And gradient over the entire data set is impractical. If we have a very large scale data set, like ImageNet, we have millions of data. If you have a small data set, like hundreds or thousand data set, maybe, accumulate the loss over all the samples in the data set is possible and compute the gradient. But for like million scale or even larger scale data set, doing this over the entire data set is impractical because it will take a lot of time. So what we want is we need to take a quick approach, but it's not perfect, but maybe we can consider this noisy, right? So that's why this is called this stochastic gradient descent. Instead of choosing the entire data set, we can sample a small subset. We call this mini batch, right? Let's say 100, right? Instead of considering a million of samples in the entire training database. So we can estimate the gradient over this mini batch of examples and quickly update the model parameters. So in this case, we can, quickly, get these iterations and update the network parameters towards a local minima. So here is basically how we can using the take the mini batch to do the optimization. right? So let's again consider this digit classification problem. And let's say we have 100 of image, 100 of total images, and we still want to using the mini batch to quickly optimize the network parameter, right? So first we can decide, right, how many images going to be there in a mini batch. Let's consider, 10 images in a mini batch. In this case, we can divide those, a total of 100 image, into 10 batches, right? In each batch, we'll have 10 images. So during the optimization, then we'll pick, the first batch and, get the loss for those 10 samples and compute the gradient and update the parameter, okay? And next iteration, we can pick the second batch and do the same, right? Compute the loss over those, another set of 10 images and update the parameters. And, we can do this up till we kind of pick all the batches we have. And in this case, we kind of iterate over all the examples, all the samples in the training data set, right? Which is those 100 images. So the whole process we consider one epoch. And of course, we can repeat the whole process, right, for many training epochs, right? So you often heard, right, how many training epochs, for the model to converge, right? So this is this concept come from, okay? Here I just give you an example, right? So typically in the when you write a code, you have to specify these hyperparameters, right? What's the batch size you want to use, right? 100 or 200, or any other numbers you want to use, and how many training epochs you want to do, right? So one epoch is going to be iterate over all the training samples in the database. Okay. Okay, so we've talked about the classic stochastic gradient descent, right? So there's obviously other advanced optimizers, people use very often. So one is called the ADAM. So this is a very popular, very effective optimizers people widely used. So I highly recommend you check this, the original paper, and in your maybe assignment or project, and you can also try this ADAM optimizer, right? And maybe do a comparison of with ADAM and SGD, right? And see what's the benefit of using ADAM, or maybe in some cases, SGD may still are very competitive as compared to ADAM. Okay. Okay. So we kind of touch upon like the process of set up the network and how we can train the network, right? So we know the basic step we have to take to get to optimize network so that the model we learn can be used for inference. So we also mentioned a couple of hyperparameters, right, which we need to optimize. One important hyperparameter is the learning rate, right? So this alpha value in this gradient descent we've talked about. And this is important is because it will affect the learning process, right? If you specify a large learning rate, and you may end up the model, kind of diverge, well, never converge, or converge very slowly. And if you have a small learning rate, then you end up with a very slow convergence. So here, let me quickly, give you a example. What does this mean, right? So let's consider you may have you have a loss curve may look like this, right? So let's say you have when you do the optimization, right? So here, this is our goal, right? We want to reach this local minima, right? Or in this case, this is the global minima, right? So we want to have a proper learning rate, right? So for the gradient descent, we can take some steps, right? Gradually, going towards these global minimum direction, right? We want to go downhill. Eventually, after certain steps, we can reach here, right? And remember the learning rate, right? So the alpha, minus alpha with the gradient, right? So if you have a large value here, alpha, which means you will take a large leap, right? So here you may going here, right? You take a large jump. In the beginning, this may be okay, right? Maybe you have a high loss here, and you take a large leap towards direction, and you will see maybe your loss decrease very sharply, right? You take a couple of steps, you're able to minimize your loss significantly, okay? But the problem is that, okay, for this case, right, you end up here, you're very close to the global minima in this case. But if you do one more step, right, you may have the risk of overshoot because you take a large step, right? You overshoot to this side, okay? You end up here, right? You're not taking proper step toward this global minima. You'd end up here. Then you take another step, then you may jump here, okay? So in this case, you just jump back and forth in this valley, right? Because, up till to the end, right? Because of these large, learning rate, large step you'll take, you will always jump over this global minima. This is not the case we want, right? We want the model to converge to a local minima at least, okay? And if this too small, right, slow convergence, this is easy to understand, right? You take a very small, tiny baby step towards these global minima, right? Then you need to, spend a lot of steps to reach there, right? This is not we want either, right? You may end up getting this global minima or local minima, but it's take too much time to get there. So in practice, there's no a single learning rate, can rule them all, right? You cannot specify a single learning rate which can give you this optimal result. Typically, there are some strategies we can take, right? So maybe in the beginning, we can specify a relatively high value, right? Because, the network is randomly initialized, right? The loss is going to be very high. So it's safe to say that we can take a few large steps to quickly go near this local minima, right? Then we can cut on, or reduce the learning rate a bit, right? To trying to, reduce the step you jump, leap forward, so that we can adjust how much we move, right? So hopefully we are able to gradually, go to this local minima and avoid overshoot, right? So in practice, we can actually using a learning rate schedule, right? So like after how many training epochs you want to decrease by an order of 10, right? Let's say in the beginning, you have a large learning rate, 0.001, okay? This is a typical learning rate people use, or even a smaller number. And maybe after 10 or 20 epochs, right, you can decrease to 0.001, right? And you can do this for a couple of schedules, so that you kind of take very precaution, right, trying to get close to the local minima as as effective as possible, right, to avoid this kind of overshoot problem. So these are some of the strategies, to how we can tune this learning rate to optimize the network, okay? And in this figure, I show a couple of scenarios, right? If you have, different learning rate, what might be the loss look like, okay? So if you have a high learning rate, like draw in the previous slide, right? You may end up diverge, right? So you never converge to a local minima. So your loss always, jump back and forth, even going higher, right? Because you're jumping towards the high point. And if you have a low learning rate, right? So then you take a lot of steps, to converge to the local minima, right? So you have to train a very long training epochs. And if you have a higher learning rate, not considered very high, right? You're still gonna be, able to reach local minima, but because you have a high learning rate, maybe that local minima is not very good, right? Because in the loss landscape for the network can be very complex. You end up with, there's going to be many local minima, right? But in this case, you may end up not a so good one. But you can see that a high learning rate will get you quickly to reduce the loss, right? So here and then you plateaus here. So a good learning rate is that, right, you gradually decrease the loss and eventually it will hopefully will get to like the optimal local minima you can reach. Okay. So another issue, as Wang Yu mentioned, right? So if you have a large networks, usually is over parameterized, right? Have a lot of parameters to optimize, and how can we train a stable network is very important, right? And so we need some of the technique to regularize the training, right? And overfitting is one serious issue. The overfitting means the network is trying very hard on the training data set, right? Trying to reach maybe 100% accuracy on the training data set, but when we're using that model to do the testing, it's not able to generalize well. You have a very bad test accuracy because the overfitting means the model may be too complex, right? Only fit well with the training data, but the tested data may have some small difference, right? The distribution may be changed a bit, right? But in this case, the model is not able to adapt very well. So we want to avoid that, right? So there's a couple of strategies we can use to regularize. So one is we can use dropout, and we can using the weight decay or L2 regularization. So which is basically here, right? So instead of using the loss, we also want to add extra term, right? This is the magnitude of the weights, right? How large is the weights, right? So in this case, we want to penalize a large weights in the network parameter. So why do we want to penalize large weights? The reason is that, if you have a large weights, the network training is not going to be very stable and often is a sign of overfitting, right? Think about this. If you have an input which, makes small changes, right? And if you have very large weights, then we'll end up with maybe a large change in the output, right? This is not the ideal case. Like I mentioned, right, in the test data set, you have some changes, right? You are not going to get the same data as your training set. So we want the network is able to handle or be very robust to these kind of small changes, right? But this large weight is going to be problematic, right? So that's why we need to use some regularization to penalize these large weights, okay? And another strategy is commonly used is the early stopping, right? So you've heard of like we have training set, validation set, and the test set, right? So we can using validation set to monitor the training the loss, and at some point we can stop the training properly. So here is a figure to show what I mean by early stopping, right? So this the blue curve here is the training curve, right? So the loss or the error keep reducing. If we don't look at the validation error, right, you may think, okay, this is a good sign, right? Because we keep reducing the error, right? And the network is making more and more accurate prediction for the training data set. But this is not always the good case. As I mentioned, the risk of overfitting, right? You're trying too hard on the training data set. You're trying to be very perfect on the training data. You end up with a very complex, decision boundary or decision function. So this may not be fit well for the test set. So what we do is we set aside a validation set, maybe a small subset as the validation. We also have the ground truth, right? So every time, during the course of the training, right, maybe every epoch we can test what's the error this model is making on this validation set, right? So here we actually observe, right, at this point, although the training error is still decreasing, but the validation error is going up, right? So this is a sign that okay, if you keep training, then there's a risk of overfitting. So we want to stop here, because here validation is kind of act like a way, mimicking the test set, right? So here, this is the right amount of the optimization we need, so that on the unseen test set, we are still able to achieve a better job, okay, as compared to you reach here. The validation error is going to go up a lot, okay? So for the dropout, it's also a way to kind of doing the regularization and preventing overfitting. So during the training, each time, before we updating the parameter, we can actually randomly drop out a couple of neurons, right? So here we can specify a probability, of each neuron can, drop out, right? Which means you can disconnect this neuron, right? So disconnect this connection, okay? As if this neuron was not there, right? This path has been disabled, okay? So each neuron has a certain probability to drop out during the training. So you may end up as a different network structure, a little bit sparser, right? Because we drop out some of the neurons. And the structure is changed, right? So we can train this, and because we specify each neuron has a certain probability to be drop out, right? So you may, at a different training iterations, you may have different network structures, right? In this iteration, these neurons have been dropped out, but in the next iteration, it may come back, but the other neurons may be drop out, right? So you end up with different structures every time. So we can train in this way. The rationale behind it is that, if you always keep all the neurons there, right? Maybe some of the neurons trying to team up, trying to accomplish a goal, right? So it depending on each other, right? These 3 or 4 together to, trying to capture some important information. But in the ideal case that we want each neuron is able to learn or discover some of the information from the data, right? Each of the neuron has a certain or have a very strong representation capability, right? So we force them to, without teaming, right? So every time we disable some of the neurons, so that each neuron will force to learn meaningful representations during the training process, okay? So kind of like make everyone getting stronger and stronger, right? Rather, you have to together, to perform a certain or capture certain information from the data. So during the testing, we don't do dropout because it's not necessary, right? Because during the training, we train this neuron to be the best by its own, right? Then in the testing, we want to leverage all of them. Hopefully, we're able to learn very well from the data and do well on the test set. In a way, you can think about dropout is a kind of ensemble, right? So because in the training, we disable some of the neurons, right? We change the structures, right? We can consider these different networks, and we are doing this kind of ensemble training. And this ensemble learning usually will give, stronger or better performance. Okay. So if you're interested into learning more, right, training the CNNs or some of the details, here I list a couple of, reading materials you can read to, right? So there's a, step-by-step, coding examples, right? How you can do maybe like SAFAR 10 image classification or digit recognition, digit classification from MNIST, okay? And also there's a very nice paper list a couple, like a bag of tricks, right? How you can train the convolutional neural networks, right? What kind of, batch size you should specify, right? Or what kind of learning rate you can specify according to the batch size you have, right? What other technique, like, learning rate schedules usually perform better or perform well. So those are some of the tricks. You can read this paper and maybe apply them during the project or assignment, okay? And I also want to mention this latest GitHub repo is coming from Google Research. So this is called this deep learning tuning playbook. So basically, they're also trying to give you a couple of examples or like the general rule of thumbs to tune these hyperparameters so that you can maximize the performance of the deep learning model. So I also highly recommend you can check this out, and maybe you can find this useful. And some of the tricks may be useful for your research. Okay. Okay. Finally, I want to also mention another very popular technique has been used a lot in image classification. So that is data augmentation. So data augmentation also can be considered a kind of regularization, right? So these kind of dropout, weight decay, those can be considered as network or internal regularization, right? Based on the network. Here, the data augmentation, you can consider this is a data level regularization, right? As we know that if you have a small data set, you have a large network, right? So there's a risk of overfitting because you have a highly complex network, but you will have a limited training data. But if you expand your training data, then the risk of overfitting can be mitigated at a certain extent, okay? So the data augmentation, the direct goal is to increase the training data, right? So there's a couple of very simple, straightforward strategies we can use. So here I list a couple of them. So this is the mirroring procedure that take the image and do the mirroring, right? So you generate another image, and you can do the random cropping, right? So basically you crop a small region, and the size can vary as well, right? You have a larger size or smaller size to crop, and you end up getting more images, right, corresponding to the same object, right? And you can do also other image processing step like rotation, shearing, local warping, etc., right? So you may get image look like this, right? So this is like a rotation and some of the local warping. So these are the common techniques you can use to increase the data and do the data augmentation. We can also do the color shifting, right? So basically you can adding perturbations to the different color channel, right? RGB, so that you end up with images may look visually different, right? So some maybe has a very reddish background of the object, or some maybe you have adding more values to the green channel, right? So you have looks greenish or bluish. So these are color shifting. And you can also do color space conversion, right? So we have the RGB, HSV, right, and YUV, different color spaces. You can also converting the image into different color space and using that as a new image, right, as an augmentation method. And here another augmentation strategy is random erasing, right? So the cropping is that we crop a region out from the original image and use that as a new image, right? So this random erasing is that you specify a region and you crop out this part, right? You kind of think of this like a masking, right? You remove this small region and you take that as a new image. You can specify different shapes, right? Maybe this is square, rectangle at different positions and different aspect ratios of this rectangle, okay? So, but here you may be wondering, right, why in this case this is useful, right? You erase some of the regions in the image, why this is going to be helpful. So you can think about, right, so if this image, I erase some of the very important characters of a specific object. Yeah, let's say this is I think a fox image, right? Let's say the most important characteristics to recognize or determine this is a fox, maybe this is the nose or the ear, right? So if we remove this part, right, the network will try harder to look into other characteristics or other body parts to help the network to learn, okay, this is a fox, right? But if you're only using this, then the network may only consider or learn to using or remember the ear shape or the nose to recognize this is a fox, right? So maybe this is not good enough, right? So you want the network trying to learn other different things that is also able to determine this is a fox. So in this case, the network is going to be more robust. And here in this paper, they also instead of doing like these handcrafted, designed strategies to do the augmentation, they learn the augmentation policies from the data, right? So they're using a set of operations, and they train a policy using reinforcement learning, right? What kind of operations we can do so that the augmented data can mostly help the model training, right? So maybe you should apply translation first, then do the rotation, then do the contrast, brightness change, or sharpen change. Then the end result, augmented image, will help the most for the training. So they come up with a strategy to automatically learn the augmentation policy from the data and do the auto augmentation. Okay. And here is a comparison, right? Just to give you some idea, right? How this kind of augmentation strategy is able to help improving the classification accuracy, right? So you can see that there's different augmentation strategy like mix up, cut out, cut mix, right? So specifically this cut mix method is able to improve the ImageNet classification by 2.3%, right? So this is considered a lot, right? Because in ImageNet, improving 1% is sometimes very difficult. So by doing this simple data augmentation, using the same network, doing the training is able to increase 2.3%, which is very good. Okay, so for these different augmentation, operations or transformations, you don't have to implement yourself. So these are like PyTorch or TensorFlow. They have these built-in, functions that you call this torch vision transforms. They were able to apply these transformations as the data augmentation approach. Okay. So finally, I just want to briefly mention a couple of classic or widely used deep convolutional neural network architectures. So first is the AlexNet, right? That's the most popular, get the deep learning excited or very popular due to the success of AlexNet winning the ImageNet competition. Then the VGGNet from Google, and also the Inception network using different kernel size together as the like a main novel module in their network. And of course, we have the ResNet, which is right now widely used for a lot of applications, not just classification, but also other tasks like detection and segmentation. So the one significant contribution for the ResNet is introduce this skip connections, right? So you can directly have the input of X to the next layer, right? So effectively, you just these layers just learn the residual, right? So in this case, some of the study mentioned that if we want to building a deeper network, right? So the vanishing gradient is always an issue. But if we are able to introduce this kind of skip connection, it will help the back propagation, right? Because by introducing this kind of short path, it will carry gradient throughout some of the previous layer, right? So that you still have the gradient flow if you have a very deep network. So yeah, so if you're interested, you can read this paper. They have this kind of insight why ResNet is to some extent is able to prevent this vanishing gradient problem. Okay, so finally, these are some of the models integrated in these common deep learning frameworks like PyTorch. So these are a couple of them, but I mean there may be more here. So you just have to kind of call these, use these models. You don't have to build or implement yourself. Okay, so this is Torch and Keras. They also have these models. Okay,